Hello, my name is Brian Heitner, and welcome to my presentation on unit testing. This is part of an individual project. I apologize, exploring the crucial role of unit testing in software development. Unit testing is often underestimated, yet it plays a foundational role in building robust, reliable software systems. I'll be explaining for the fundamentals of unit testing, what it is, why it's important, to the tools and techniques we use, such as JUnit and Mockito. Alright, let's get started. Before diving into the details, here's a quick overview of what we'll be covering. This presentation is structured to first build a strong conceptual foundation, and then gradually move into more practical and technical technique aspects. We'll begin with explaining what unit testing is, why it's important, some core concepts and terminology that's often associated with it, good unit tests versus bad unit tests, and also comparing it to other types of tests, like other ones. JUnit and practical examples, mocking with Mockito, common pitfalls that can arise with it, and we'll be diving a little bit into test-driven development, or TDD. Unit testing is, in simplest terms, a software testing technique where individual pieces of code, usually functions or methods, are tested in isolation. A unit refers to the smallest testable part of a code, usually functions or methods, and it's typically automated and run by developers, and it falls into the broader software testing lifecycle, which includes integration, system, and acceptance testing. Unlike those types, unit testing focuses exclusively on internal correctness. Does this one function on its own behave properly given some inputs? Why is unit testing important? Now that we know what it is, let's talk about why it matters so much. First and foremost, unit testing helps us catch bugs early in the development process, when they're easiest and cheapest to fix. A bug found during development is far less costly than one discovered in production. I guess that note hasn't been passed on to modern game developers, but that's besides the point. But it's not just about catching bugs. Unit testing improves overall code quality, like for example, getting rid of negative space, making it more efficient and more optimized. Writing code forces developers to write code that is modular and deoccupied, because such code is easier to test with. It encourages you to design your code in small, focused functions that do one thing well. So basically, one-trick ponies. Martin Flower, a leading figure in software engineering, points out that unit tests are crucial for enabling change. When you have a solid test suite, you can refactor code confidently, knowing that if you break something, your test will catch it. This leads to more maintainable software and makes long-term evolution of the system possible. Unit tests also serve as living documentation. When someone new joins a project, they can read the test to understand what the code is supposed to do. Unlike traditional documentation, which quickly becomes outdated, tests are kept current by necessity. They fail if expectations change. Finally, unit testing helps foster a culture of quality with a developer's team. When tests are a natural part of the workflow, quality becomes baked into the development process itself, rather than being something tacked on at the end. In regards to other types of methods, like ones I just mentioned, unit testing, as we've discussed, has the smallest components of an application in isolation. While integration testing is a step up, it checks whether different modules or services work together. For example, if one function relies on data from another, an integration test would check whether they interact correctly. System testing evaluates the application as a whole. It simulates user workflows and verifies that all parts of the system integrate and behave as expected. This is often done by quality assurance teams. Acceptance testing is even broader. It validates whether the system meets business requirements from the end user's perspective. These tests are often written in collaboration with product owners or stakeholders. You can think of unit tests as the foundation of a testing pyramid: small, numerous, and fast. Integration and system tests are fewer but broader in scope and slower to run. Getting unit tests right ensures the foundation is solid, making higher level testing smoother and more reliable. Now the anatomy of a unit test. There's setup, execution, assertion, and teardown. Let's begin with the setup. In the setup phase, we initialize the objects or values that the unit that the unit under the test needs. This might be creating an instance of a class, setting up input parameters, or configuring a test environment. The execution phase is where we actually run the method or function being tested. This is a core part of where we invoke the behavior of what we want to test. Next comes the assertion phase. Here we compare the actual output of the execution step to our expected output. Assertions are statements that must be true for the test to pass. If an assertion fails, the test fails. Finally, there's the teardown, which is usually used to clean up resources if need be. In many unit tests, especially in Java using JUnit, teardown isn't always required because tests are typically run in isolated environments. In JUnit, which we'll look at more closely soon, we include annotations like @test to identify a test method. We also have before each and after each for setup and teardown. The use of these annotations makes the structure explicit and helps ensure the test remains consistent and repeatable. Now, what makes one good, effective? It has to be, like we discussed earlier, it has to be fast, isolated, and repeatable. It has to be self-validating and readable, and avoid flaky or hard to maintain. And we need to avoid flaky or hard to maintain tests. If a test checks too many things, uses unclear naming, or is full of setup clutter, it's harder to maintain and easier to break without realizing. So focus on clarity and simplicity when writing tests. Now we'll be talking about JUnit. Now that we understand what makes a good test, we'll be talking about a popular tool used for writing them in Java, JUnit. JUnit is a testing framework that has been around for many years and is widely used in both industry and academia. The latest version, JUnit 5, brings significant improvements in flexibility, usability, and structure. It introduces new annotations, a cleaner API for assertions, and better support for modular test organization. At the core of JUnit are annotations. The most common one is @test, which, like we mentioned earlier, marks a method as a test method. You could also use before each and after each to clean up anything afterwards and make it a bit more clear when it starts and when it ends. JUnit also uses a wide range of assertion methods, such as assert equals, assert true, and assert null, and many more. These assertions compare expected values to actual outcomes and throw an exception if the condition is not met. One improvement in JUnit 5 is that the message in an assertion now comes last, which is more intuitive for developers. So, for example, if you'd write assert equals expected actual option failure message. Sorry, that wasn't very clear. But it says expected what the actual one is, and then if there's an optional failure message. So, yeah, you get the idea. JUnit integrates seamlessly with build tools like Maven or Gradle, and it works well with IDEs like IntelliJ or Eclipse, where you can run and debug tests with just a few clicks. Overall, JUnit makes it easy to create and organize tests, and is the backbone of testing many Java applications. So, here's an example. This is a screenshot from Notepad. Unfortunately, it's not from JUnit. I just like using Notepad to write code, so this is just what I had offhand. In this test, we're creating an instance of a calculator, calling the add method with the arguments 2 and 3, and checking that the result is 5. The method, named add numbers and underscore should return sum, clearly states what the test is about. The naming convention helps in understanding the intent of the test at a glance. The assertion assert equals 5, result verifies that the output is what we expect. If the actual result is not 5, the test will fail and JUnit will report the discrepancy. This kind of test is fast, focused, and repeatable. like how it should be. It only tests the add method and doesn't rely on any external dependencies and clearly defines the expected behavior. Writing clear, meaningful assertions like this is the cornerstone of an effective unit test. Even for more complex logic, breaking it down into small, testable pieces like this ensures better reliability and maintainability. This is another example screenshotted from Notepad. This is exception handling. Unit testing isn't just about checking correct output, it's also about verifying that your code behaves correctly when things go wrong. This includes handling exceptions properly. In this example, we're making sure that dividing by 0 throws an arithmetic exception, because we want to make sure our program is as idiot-proof as possible, and an exception handling helps us, unit test it to make sure that function works. See, this is all just coming back full circle. I'm almost repeating myself at times. Now here's basic unit tests. The LinkedIn learning videos on Java, if you're to check those out, offer a solid practical foundation, especially for beginners. These lessons walk through key components like writing for your first unit test, using assertions, and managing setup and teardown code effectively. One important concept highlighted is the use of the app before each annotation in JUnit. This method runs before each test case and is commonly used to set up the objects or test environment you'll need. This helps keep test methods clean and focused, since shared setup code doesn't have to be replaced. Another feature discussed is using the nested classes in JUnit 5. These allow you to group related tests together, which improves organization and readability. For example, if you're testing the behavior of a login function under different conditions, you might group all these tests together in a nested class named login tests. The videos also walk through writing tests for edge cases and exception handling, which we've already touched. These practical demonstrations reinforce how unit testing becomes a habit, not something you just do occasionally, but something baked into your coding routine from the beginning. Now we're going to be mocking with Mockito. So we're going to be simulating behavior dependencies. Mockito, just as a rundown of what Mockito is, it's a popular Java library used for mocking, that is, creating fake versions of objects that simulate the behavior of real dependencies. Let's say if they had to access a database, for example. This lets us, instead of having to access a specific database, this just simulates activating a database. It mocks it, if you will. Funny how that works out. Martin Fowler explains that mocks aren't just stubs. While stubs return predefined data, mocks can also verify interactions, like checking if a method was called, how many times, or with what arguments. This allows us to not only test the outcome, but also ensure that the behavior of our code is correct. Using mocks leads to tests that are faster, more reliable, and more focused. The foundation of unit testing, you heard this all before, they let us concentrate purely on the logic inside the unit we're testing, rather than the behavior of its collaborators. Here's an example of mocking. Again, this is from Notepad. So let's walk through the code example. In this test, we're testing a user service that depends on user repository to fetch user data. Instead of using a real repository, we mock it. So at test, void test user, user repository mock repo, mock user repository class, all that good stuff. Here's what's happening. We create a mock user. We create a mock of user repository. We tell Mockito, when the method findUser by ID 1 is called, return a fake user object with the name Alice. Then we pass the mock repository to our user service. Finally, we call the getUser method and check that the return user's name is Alice. This test verifies that the user service correctly uses the repository to retrieve user data. We don't care how the repository works, we just want to test the logic inside the service. This approach keeps our tests simple and avoids unnecessary dependencies. It's a clear example of how mocking can make unit tests more powerful and maintainable. Here are the qualities of a good test. There are three questions it needs to break down to. What should it do? What is the setup? And expected versus actual result. So let's break it down. What are you testing? The name of the test method should describe exactly what's being tested. For example, For example, add numbers should return sum is a much better title than test that. It makes sense. What should it do? Your assertion should clearly state what the correct behavior is. This sets expectations for future readers and maintainers. Again, you want this to be as easy to read as possible. It's meant to be documentation as well. What's the setup? You should initialize any required objects or data needed for the test. Use methods like at before each to avoid repetition. What is the expected result? This should be explicitly written in your test, often via assertion. What is the actual result? The test runtime compares this with the expected result, and if they differ, the test fails and alerts you. Following these principles ensures your tests are clear, useful, and trustworthy. They also act as real-time documentation for your code and expectations. If someone changes the code in the future, these tests will serve as guardrails and help them understand what's supposed to happen. Alright, so let's now get a little bit into test-driven development. One of the most powerful uses of unit testing is test-driven development, or TDD. This methodology flips the usual development process on its head. In TDD, you start by writing a failing test before you even write any code. This test defines the behavior you want. Then you write the minimum amount of code necessary to make the test pass. Finally, you refactor the code while making sure the test continues to pass. This is often described as the red-green refactor cycle. TDD has many benefits. It encourages developers to think clearly about the requirements and edge cases before implementing logic. It leads to simpler, more focused functions because each one must be written to pass a specific test. It also means you build up a comprehensive test suite alongside your code. Martin Fowler emphasizes that TDD is more about design than testing. It encourages better architecture and modularity because you're forced to write testable code. Of course, TDD doesn't work in every situation, especially when prototyping or exploring a new idea. But for developing business logic, libraries, or APIs, it's a disciplined approach that leads to better results and fewer bugs. Challenges and pitfalls. While unit testing is a powerful tool, it's easy to fall into a few common traps that reduce its effectiveness. One of them is overmocking. While mocking is useful, using too many mocks can lead to fragile tests that are tightly coupled with implementation details. A good rule is to only mock when you absolutely need to isolate. Another issue is writing overly complex tests. They need to be simple. If a unit test takes more time to understand than the code is testing, that's a problem. Keep your tests small and focused. Each one should verify just one behavior. Like the examples we made up earlier, like with the calculator making sure that add works as intended. Then there's also flaky tests. Tests that pass sometimes and fail other times. These often result from shared state between tests, randomness, or reliance on external systems. Flaky tests erode your trust in your test suite and can slow down development. Ignoring edge cases is another trap. Your test should verify not just the happy path, but also invalid inputs, null values, or error conditions. Finally, some developers skip unit tests altogether, assuming manual testing or QA will catch everything. But skipping unit tests means giving up on early feedback, missing bugs that could have been caught in seconds. So basically, by doing it, you're pretty much wasting everyone's time in the long run. It may take more time now, but it really shouldn't take you too much time. In conclusion, unit testing involves writing small, fast tests that verify individual pieces of code in isolation. These tests help catch bugs early, improve code design, and act as living documentation. We discussed the structure of unit tests, including the setup, execution, and assertion. We reviewed what makes a test good. It should be fast, isolated, readable, and repeatable. So it needs to be FIRR. I just came up with that on the spot. I'm pretty proud of it. We explored tools like JUnit for structuring tests and Mockito for mocking dependencies, enabling us to test code without relying on external systems. We also examined how to write assertions and test exceptions properly. Test for exceptions properly. We talked about test-driven development, which uses unit tests to drive design, and we went over some common pitfalls to avoid, like overmocking or writing flaky tests. In essence, unit testing is not just a coding activity, it's a mindset and a part of the process. It encourages thoughtful design, builds confidence in your code, and leads to more stable and maintainable software. These are the sources I drew from. I also referred to Wikipedia articles, but Wikipedia admittedly isn't the best source, so it's best to go deeper than Wikipedia. Oh, sorry. I hope this helped you understand not just how to write unit tests, but why they are such a vital part of the software development. If you're interested in learning more, just refer to any of the sources that are on screen. Thank you and have a good day.